At 10:47 p.m., the ocean floor off Japan snapped. A magnitude 7.5 earthquake tore through the Pacific, and within 4 minutes tsunami alerts were screaming across phones, speakers, and emergency systems along the northeastern coast. 90,000 people were ordered out into the dark. The same coastline that was swallowed in 2011 was bracing again. Waves began to move, sirens echoed, and for a few breathless minutes the world wondered if history was about to repeat itself. But here's what makes this different and far more unsettling. Beneath the rupture zone along the Japan Trench, scientists previously uncovered something no one expected: a 100-meter thick layer of ultra-slippery pelagic clay buried deep inside the fault. During the 2011 Tohoku disaster, that hidden layer acted like grease between tectonic plates, allowing the rupture to rocket upward and physically lift the seafloor, unleashing a monstrous tsunami. Tonight, that same fault system moved again. The 70-centimeter waves may not be the headline. The real question is this: did this earthquake touch that same buried weakness? Because if it did, this may not be the end of the story. When the shaking began, it did not stay offshore for long. Seismic monitoring stations across Japan detected the rupture within seconds. The epicenter was located roughly 40 kilometers off the coast of the Noto Peninsula, at a depth that immediately caught the attention of analysts tracking activity along the Japan Trench. This is not just another fault line. It is one of the most active and closely watched subduction zones on Earth. At 10:51 p.m., just 4 minutes after the initial rupture, the Japan Meteorological Agency issued a tsunami warning. 4 minutes. That was the window coastal communities had before emergency alerts erupted across phones, television broadcasts, and loudspeaker systems. The message was not advisory. It was immediate evacuation. Nearly 90,000 residents across Ishikawa, Toyama, and Niigata prefectures were ordered to move to higher ground. In coastal cities like Wajima, evacuation centers opened within minutes. Families grabbed emergency kits prepared years earlier. Elderly residents were assisted by neighbors. Volunteers guided traffic toward designated safe zones. The choreography of disaster response rehearsed for decades unfolded in real time. By 11:03 p.m., offshore tsunami monitoring buoys began registering wave activity. At 11:19 p.m., waves, measuring approximately 70 centimeters, were confirmed along parts of the northeastern coastline. 70 centimeters may not sound catastrophic. It is not a towering wall of water, but at tsunami speed, even a wave of that height carries immense force. It can knock adults off their feet, flood coastal roads, damage fishing infrastructure, and push debris inland with surprising violence. And more importantly, early wave measurements do not always represent the maximum surge. Japan's self-defense forces mobilized within the hour. Helicopters were deployed along vulnerable stretches of coast. The Japan Coast Guard repositioned vessels in case search and rescue operations became necessary. Crisis response centers activated full emergency protocols. On the surface, the response worked. Sea walls held, evacuation routes functioned, casualties were avoided. But beneath the ocean floor, seismologists were studying something far more complex than wave height. They were analyzing rupture, depth fault, geometry, and slip behavior, trying to determine whether this earthquake remained confined to deeper rock or whether it traveled upward along a pathway that has rewritten scientific understanding before. Because in this region, the difference between deep rupture and shallow rupture can mean the difference between a warning and a catastrophe. To understand why this coastline reacts so quickly to seismic movement, you have to look at the structure beneath it. Running parallel to Japan's eastern shore is the Japan Trench, a massive underwater boundary where the Pacific Plate is slowly forcing its way beneath the Eurasian Plate. The motion is gradual, only a few centimeters per year, but the pressure it builds is enormous. Over time, sections of the fault lock together. Stress accumulates silently, invisibly, until the rock can no longer withstand it. When that lock finally breaks, the release is sudden and violent. In March 2011, that release became the Tohoku earthquake, a magnitude 9.0 rupture that tore along hundreds of kilometers of fault. What stunned scientists was not just the strength of the shaking, but how far the rupture traveled toward the surface. The shallow portion of the fault moved dramatically, lifting the seafloor and displacing an immense column of water. That vertical shift generated a tsunami, reaching heights of up to 40 meters in some areas, devastating coastal communities and triggering the crisis at the Fukushima Daiichi nuclear power plant. The lesson from 2011 was clear: in subduction zones, depth matters as much as magnitude. A rupture that climbs toward the seafloor can transform strong shaking into overwhelming waves, and that geological reality still defines the risk today. After the 2011, disaster scientists realized that computer models were no longer enough. Something about that rupture had defied expectations. The shallow portion of the fault had moved far more easily than theory predicted. To understand why, researchers decided to go directly to the source. An international team positioned the deep-sea drilling vessel Chikyu above the rupture zone along the Japan Trench and began drilling into the seafloor itself. The mission pushed engineering limits, penetrating deeper beneath the ocean floor than any scientific expedition before it. What they retrieved were core samples, cylindrical sections of rock and sediment pulled from the very fault that had generated the 2011 Tohoku earthquake. Inside those cores, researchers discovered a roughly 100-meter thick band of pelagic clay. It was soft, fine-grained sediment that had accumulated slowly over millions of years. At first glance, it looked insignificant. But laboratory tests revealed something critical under intense pressure. This clay had extremely low friction. In a megathrust earthquake, friction controls how far and how fast a rupture can travel. Hard rock resists movement. But this clay behaved differently. It acted almost like a lubricant between tectonic plates. When the fault slipped in 2011, the rupture did not grind to a halt in the shallow crust. It accelerated along this weak layer, racing upward until it reached the seafloor. That shallow slip allowed the ocean floor itself to shift dramatically, displacing massive volumes of water. The result was not just shaking, it was vertical uplift of the seabed, the direct trigger for the catastrophic tsunami. This discovery changed how scientists calculate tsunami risk, revealing that hidden geological layers can amplify destruction in ways once thought unlikely. Now, the critical question is not what happened in 2011. It is what happened tonight. The magnitude 7.5 earthquake that struck offshore did not match the scale of the 2011 Tohoku disaster. The recorded 70-centimeter waves were significantly smaller. Coastal defenses held. Evacuations were successful. On the surface, this event appears contained. But seismologists are not focused only on magnitude or wave height. They are examining rupture depth. Early seismic data places the event within the broader fault system of the Japan Trench, the same subduction boundary where the pelagic clay layer was discovered by the drilling mission of the Chikyu. What scientists are now analyzing is whether this rupture remained confined to deeper rock or whether it propagated upward toward the shallow zone where friction drops dramatically. Depth changes everything. A deeper rupture releases energy primarily through shaking. A shallow rupture, especially one interacting with low-friction material, can transfer more displacement directly to the seafloor. And even moderate vertical movement can produce disproportionately large tsunami signals under certain conditions. The 70-centimeter waves recorded tonight are being treated as geological data, not just coastal measurements. Wave height reflects how the ocean floor moved. By reverse engineering the wave patterns, researchers can estimate slip distribution and deformation at depth. If the rupture did not engage the shallow clay layer, the immediate tsunami risk remains limited. But if even part of that weak pathway was activated, it may alter stress conditions along adjacent sections of the fault. That does not mean a larger earthquake is imminent. It means the system has shifted. And in subduction zones, every shift matters. The implications of this discovery do not stop at Japan's shoreline. The Japan Trench is only one segment of a vast tectonic network encircling the Pacific Ocean, the Ring of Fire. Subduction zones with similar geological structures exist beneath Cascadia in North America, along the coast of Chile, across Indonesia and near Alaska. Each of these regions is capable of producing megathrust earthquakes. Each has coastal populations that depend on accurate tsunami modeling. The lesson from the pelagic clay discovery is not that disaster is inevitable. It is that hidden variables matter. If low-friction sediment layers are present in other subduction systems, they could allow shallow slip to travel farther and faster than previously modeled. That would increase the likelihood of significant seafloor displacement, the key ingredient in generating powerful tsunamis. Researchers are now re-examining seismic data and sediment composition from other trenches with renewed urgency. Advanced imaging techniques and offshore drilling missions are being used to search for similar weak zones buried beneath kilometers of ocean. Mapping is incomplete. Many fault systems have never been sampled directly at this depth. Tonight's magnitude 7.5 earthquake serves as a reminder that scientific understanding is still evolving. The clay layer discovered after the 2011 Tohoku disaster reshaped tsunami risk assessment in Japan. The next step is determining whether that insight must be applied globally, because if one coastline was underestimated before others could be as well. The waves from tonight's earthquake have receded. Tsunami warnings have been downgraded. Families who fled into the cold darkness are returning home. By every visible measure, Japan's emergency systems worked. Years of preparation after the 2011 Tohoku disaster proved their value. But preparedness does not change geology. Beneath the Pacific Ocean along the Japan Trench, the tectonic plates are still locked in slow motion. The pelagic clay layer discovered by the crew of the Chikyu remains buried inside the fault, silent, compressed, unchanged. It waited millions of years before amplifying one of the most powerful earthquakes in recorded history. It is still there now. Tonight's magnitude 7.5 event may ultimately be remembered as a warning rather than a catastrophe. A reminder of how quickly calm can shift to crisis. A reminder that magnitude is only part of the equation. The earth beneath Japan does not simply shake, it stores pressure. It follows physics written long before modern cities stood along the coast. And somewhere in that darkness beneath the seafloor, the pathway that once unleashed a devastating tsunami still exists. The only uncertainty is timing. Subscribe now, like this video, comment below, share your thoughts. Join our community, turn on notifications, support the channel, stay updated. Follow for more, hit like, drop a comment, tap subscribe, don't miss out, engage with us, share and support.